First, let me say that some of us can speak either way, English or Greek, so feel free to use the translation service or ask questions in either language, and we'll respond if you like. My name is Stamatis, Krimigis, and I'm supposed to be organizing the panel and chairing. The title is, you can see, Climate Change, Earth and Space. And you might say how these things go together. Well, climate change is a fact of life that everyone knows about. Earth, of course, is the subject of all of our concerns, and the last piece is what have we learned from the exploration of both Earth and the planets. And that is what we're going to be talking about. We know that there are rising sea levels, intensified storms in the present and recent past, epidemics, including, in fact, epidemics that are not necessarily seen as part of climate change, but will have an effect, like the epidemic of overweight population, which is evident in children in Greece. If you hear from the doctors, they will tell you that. And the question is, what are the long-term prospects for establishing a long-term presence as well as advertised, and we'll talk about that at the end, in some neighboring planets, which one reads about, but hardly ever with any numbers. So to address these issues, we're going to start from right here at home, from the surface of the Earth. And we have an excellent panel. Professor Costas Synolakis is known worldwide for his work on catastrophes, including tsunamis. He's always quoted in the New York Times about the latest tsunami and what the effects might be, and I will not belabor the point very much. And then Professor Antonia Trichopoulou, who just came back from Cornell, I think, where she was honored for her work. And as some of you, at least in this audience, might know, she is the sort of the person that formulated and propagated the Mediterranean diet, which is well known all over the world by now. And she is the keeper of all the relevant data on which all that research has been based, and maintains that database and keeps on increasing it. So, without further ado, I'll turn it over to Professor Synolakis, who will tell us about what climate change is and where we are.
Okay, thank you very much, Stamatis. I'm really, I'm really honored and privileged to be here, and particularly with two of my colleagues in the Academy of Athens, Stamatis Krimigis and Antonia Trichopoulou. And I want at first to address all those climate critics and climate skeptics who keep on saying, and maybe we can have the first slide, who keep on saying that what is happening now is part of a natural cycle of the Earth, is nothing unusual going on, and that pretty much there's nothing to worry about, and as a society we can address this. As you can see from the slide, the Earth's climate, which is moderated by the Earth's atmosphere is what makes life on Earth possible, has been fairly stable for the last 800,000 years. And then suddenly, in the last 200 years, beginning in the industrial era, what we have is a sudden spike. And this is, if you can, I'll read the numbers for you at the slide. We had about, 200 to 300 parts per million, going up and down. And then suddenly, we've jumped already in the year 2020 to 50% the value that we've had for the last 800,000 years. Is this significant? What does this tell us about the future of the planet? And some people may argue, what is the worst that can happen? Okay, we increase the concentration of carbon dioxide. You do not have to be a physical scientist to see that chart. It's going up and down, up and down, up and down, and suddenly this, to realize that the Earth's climate is getting destabilized. And this is really what worries us, the destabilization of the climate. And if I can have the next slide. No, it's not the next, the one with the dinosaurs. If we have it, a slide will come with dinosaurs. We exist, ladies and gentlemen, on the surface of the Earth because dinosaurs don't exist. Because if they did exist, they would have eaten us, pretty much. 65 million years ago, there was a Chicxulub impact, which was a meteorite came in, massive meteorite. There was a meteor impact on Earth, and that changed the climate of the Earth, and in fact, produced a mass extinction. This didn't happen over a year, over 2 years, over 5 years. There are estimates that the dinosaurs disappeared over tens of years, or even hundreds of years, and some people argue even thousands of years. The end result is that they disappeared because the Earth took it quite some time to stabilize in a new climate regime. We cannot go back and reconstruct how the Earth's climate was 65 million years ago, but we certainly can do that for the last 800,000 years. So, is this a new idea? Because a lot of people are saying, and again, I want to address those people who think that climate change, and there are still a lot of people in the society that they think it's a conspiracy or it's nothing we can do. This is an idea, and if you can pull up the slide that has the horizontal bars with the chart, that starts pretty much from the time of Fourier. Fourier is one of the greatest names in the physical sciences, lived in around early 18th century, and he had this key idea of how we analyze signals. And when we play the piano, the melody that you hear, you don't hear the individual notes, but you hear essentially a melody. Fourier was the person that actually figured out how this happens, but he also figured out that the Earth, the distance from the Sun is such that, that's the timeline. These are different. I'm not going to talk about each and every one of them. But Fourier figured out that the distance from the Sun for the Earth is such that the Earth would have to be incredibly cold had it not been for the atmosphere that produces this greenhouse effect. So Fourier had it all, and in fact, by the fact that he understood how light comes in, has different frequencies, gets absorbed, and how some radiation gets trapped on the surface of the Earth heats up. What was missing is by how much, and the other part that was missing, we're talking about this is early part of the 19th century, is the anthropogenic component. So later on, and we can go on for almost 150 years going into the year 2000, we have different scientists have started mostly in the 19th century. The whole idea was to try to understand what the atmosphere is made out of and which gases in the atmosphere trap energy. And then comes the 20th century. Before the war, there are these early estimates, and James Callaghan in the UK comes with this fantastic estimate and says that if we double the carbon dioxide atmosphere, the carbon dioxide concentrations in the atmosphere, we are going to actually increase the temperature of the Earth by 4 degrees, which was a remarkably accurate estimate. But things go to a grinding halt because nobody really can estimate what are the carbon dioxides in the atmosphere. They're not measured, and this starts being measured beginning in the 1950s because people pay a lot of attention to nuclear tests, and they want to measure radionuclei in the atmosphere. So people start measuring the concentration of carbon dioxide. And then, since then, we have the Keating curve, and we have fairly precise measurements of the concentration of carbon dioxide, and of course we know that it has increased, and this is, the numbers that we have increases yearly, monotonically, and we are where we are now. So, and most of this is, there's no question about this, it is, man-made. A key element starts in the 1990s and certainly in this century, where as a scientific community we start having the computational power to do different scenarios and ask ourselves, if we follow this path and we have this particular mix of fuels or this particular lifestyle, which includes to a large effect the food we eat, the food waste, and our personal habits, climate change, it's not just energy. It's a lot of personal decisions. It's a lot of decisions that have about food. So in the last, certainly in the last 30 years, we start having a computational power to run different scenarios and suddenly see or estimate what are going to be the effects on the surface of the Earth, on human life, if we follow one scenario or the other scenario. But I submit to you here that what is important is not so much to actually focus on one particular scenario. Are we going to have actually limit the temperature increase to 1.5 degrees, which is what the Paris Agreement says, or limit our temperature increase to 2 degrees by 2050. Already we're on the way for the 1.5 degrees. So pretty much what the big effort is right now to limit the temperature increase, limit our temperature, our carbon dioxide emissions, so we limit the temperature increase to 2 degrees. That is not the question. The question is, how much do we destabilize the climate of the Earth? And I want to bring you back to the first slide that I had of actually the carbon dioxide concentrations of the atmosphere, that they're stable over 800,000 years. And then suddenly we have this peak, and we have computational models, and we try to estimate what happens. But the reality is that we're destabilizing the climate, and we're running a giant, geologic experiment of the likes that, the world, Earth, has never seen before. We're destabilizing the climate. We're in a completely, totally new era. So the question is not whether we stay 1.5, 2 degrees. The question is limiting as much as possible, being able, going into the next century, to stabilize the climate again, so that we do not have the extreme consequences that the worst-case scenarios of climate scientists, and in fact of science fiction writers, because have no doubt modern science fiction is not about just people going into other planets for exploration and aliens coming to Earth to just look at what's happening. Modern science fiction is about what's going to be the consequence of climate change and what we're going to do to in space. So we have a plan B. There's no plan B like Obama said, but maybe we'll need that in case we screw up things so badly that we'll have to no other choice but move elsewhere.
Thank you, Professor Synolakis, for a very good introduction to how much trouble we are in. And now we ask Professor Trichopoulou to tell us what the consequences of climate change is going to be in terms of health and in terms of the food chain, for example, and whatever else he decides to tell us. Thank you. Antonia?
Thank you very much, Dr. Krimigis. I will prefer to speak in Greek since I express myself much better in my mother tongue. And I see that most of the audience, they are Greeks, okay? Anyway, there is translation for our friend from the United States. So, είμαι πάρα πολύ ευτυχής που είμαι μαζί σας σήμερα να κουβεντιάσουμε ένα θέμα στο οποίο μπορούμε να κάνουμε κάτι εμείς οι ίδιοι και δεν το κάνουμε γιατί ίσως δεν το ξέρουμε ή γιατί είμαστε πολύ δύσκολοι στις αποφάσεις μας. Το θέμα αναφέρεται στα διατροφικά συστήματα και στη σημασία την οποία έχουν στην κλιματική αλλαγή. Ο καθηγητής δίπλα μας, ο κύριος Συνολάκης, μας είπε climate change και climate change και τι θα κάνουμε. Αναρωτηθήκαμε ποτέ τι μπορούμε να κάνουμε εμείς οι ίδιοι Γιατί έχει βρεθεί ότι τα διατροφικά συστήματα, τα οποία αναφέρονται στο τι τρώμε, στο πώς παράγεται το τρόφιμο, στο πώς μεταποιείται και στο πώς διατίθεται. Και σε αυτά ο καθένας από εμάς στην καθημερινότητά του έχει σημαντικό ρόλο. Και όχι μόνο αυτό, αλλά διάφορες έρευνες οι οποίες υπάρχουν και συνεχώς προστίθενται. Διάφορες έρευνες, την επόμενη παρακαλώ, διάφορες έρευνες δείχνουν ότι το 1/3 από τον ανθρώπινο παράγοντα, ο οποίος συμβάλλει στην κλιματική αλλαγή, οφείλεται στο τι τρώμε, πώς παράγεται το τρόφιμο, πώς προωθείται, πώς διατίθεται. Άρα εκεί, όπως σας είπα, έχουμε ένα πολύ μεγάλο λόγο. Και εδώ έρχεται και δένει, κάτι το οποίο το γνωρίζετε όλοι σας γιατί είναι στο DNA σας, άσχετα αν δεν το εφαρμόζουμε πια όσο παλιά, η μεσογειακή διατροφή. Αγαπητοί φίλοι, θα ξέρετε ίσως ότι η μεσογειακή διατροφή είναι επί 6 συνεχή χρόνια σε διεθνείς έρευνες, οι οποίες γίνεται American News και το American United States Report, έρχεται πρώτη παγκοσμίως όσον αφορά τη γεύση της και τη σημασία της για την υγεία. Εκείνο το οποίο δεν είναι γνωστό είναι ότι τα τελευταία 10 χρόνια η μεσογειακή διατροφή από η καλύτερη πιθανότατα, αν όχι καλύτερη, μια από τις καλύτερες διατροφές στον κόσμο, είναι μια βιώσιμη διατροφή. Και εδώ υπάρχει επιστημονική τεκμηρίωση ότι είναι μια βιώσιμη διατροφή. Την επόμενη διαφάνεια παρακαλώ. Όχι, την προηγούμενη. Ναι, γιατί έχει γίνει μια επιτροπή από το περιοδικό Lancet, το οποίο όλοι θα το γνωρίζετε, είναι ένα από τα 1, 2, 3 καλύτερα περιοδικά σε παγκόσμια κλίμακα. Πριν από ορισμένα χρόνια είχε κάνει μια επιτροπή, τη EAT Committee, EAT, η οποία δούλεψε με τα μεγαλύτερα διεθνώς ονόματα στον χώρο του περιβάλλοντος και της διατροφής και έβγαλε αυτό το συμπέρασμα, το οποίο το πήρα ακριβώς όπως αναφέρεται στο περιοδικό, ότι η μεσογειακή διατροφή είναι μια υγιεινή διατροφή και ότι είναι ένα μοντέλο βιώσιμης διατροφής. Είναι ένα μοντέλο διεθνώς sustainable diet. Γιατί η μεσογειακή διατροφή είναι μια διατροφή η οποία βασίζεται σε φυτικά τρόφιμα, χωρίς να λέει σε τίποτα όχι, ακόμα και στο κρέας λέει ναι. Είναι μια διατροφή της ποιότητος, του τι και του πόσο. Υπό αυτήν την έννοια, να περάσω στην επόμενη διαφάνεια, ήθελα να σας θυμίσω ότι εκτός του ότι η μεσογειακή διατροφή για 6 συνεχή χρόνια αναγνωρίζεται ως καλύτερη διατροφή παγκόσμια σε παγκόσμια κλίμακα, είναι μια διατροφή η οποία αναγνωρίστηκε από την UNESCO, ενετάχθη στον κατάλογο της άειλης πολιτισμικής κληρονομιάς. Και αυτό όχι γιατί είναι υγιεινή διατροφή, αλλά είναι μια διατροφή η οποία εκφράζει πολιτισμό και η οποία συνάδει με μια μακρά παράδοση του τρόπου παραγωγής των τροφίμων. Και έτσι, υπό την έννοια ότι η μεσογειακή διατροφή είναι μια διατροφή η οποία εξορισμού είναι φιλική προς το περιβάλλον, διότι ούσα κατεξοχήν βασισμένη σε φυτικά τρόφιμα δεν έχει μεγάλο αποτύπωμα νερού, δεν έχει μεγάλο αποτύπωμα κυκλοφορίας, διότι δεν ταξιδεύει πολύ, βασίζεται σε τοπικά προϊόντα και για αυτό το λόγο είναι ένα από τους πολλούς λόγους στους οποίους αναγνωρίστηκε ως μια βιώσιμη διατροφή, ως ένα μοντέλο βιώσιμης διατροφής. Τώρα, το θέμα είναι ερχόμενοι στα καθημάς, και όταν λέω στα καθημάς ενώ σε όλους τους πληθυσμούς της Μεσογείου, είναι ότι αυτή τη διατροφή η οποία αναπτύχθηκε επί χιλιετίες και η οποία εκφράζει έναν τρόπο ζωής και όχι μόνο ένα λογιστικό φύλλο θερμίδων και θρεπτικών συστατικών, αλλά είναι κάτι πολύ περισσότερο από αυτό. Αυτή η διατροφή εγκαταλείπεται σιγά σιγά τα τελευταία 10-20 χρόνια. Και δεν είναι μόνο ότι εγκαταλείπεται, αν δεχτούμε ότι είναι μια βιώσιμη διατροφή η οποία στηρίζεται και στους τρόπους παραγωγής των τροφίμων και οι παραδοσιακοί τρόποι, χωρίς να θέλω να γυρίσουμε στο άρωτρο ή με τον παγκονοπήγαδο στο πότισμα, είναι όλη αυτή η συσσωρευμένη γνώση της παραγωγής, οι ποικιλίες τις οποίες χρησιμοποιούμε, θυμηθείτε μόνο πόσες ποικιλίες από φασόλια έχουμε, πόσες ποικιλίες από ντομάτες έχουμε και έχουμε καταλήξει στο να τρώμε μία. Τα 150 άγρια χόρτα, τα οποία είναι μια τεράστιος εθνικός πλούτος, τα 100 και άνω φυτά, τα αρωματικά φυτά, τα οποία είναι για τέλεια και όλα αυτά, αυτά μένουν και ανεκμετάλλευτα, αλλά δεν είναι μόνο ότι μένουν εκμετάλλευτα, χάνεται ο τρόπος παραγωγής τους και επεξεργασίας τους. Έχω μόνο 8 λεπτά, μπορούμε να κουβεντιάσουμε πολύ περισσότερο από αυτό, αλλά θέλω να σας επισημάνω ότι ναι, ο τρόπος που τρώμε, ο τρόπος που παράγουμε το τρόφιμο έχει τεράστια σημασία, ναι μεν για την υγεία, αλλά ξεχνάμε ότι με αυτόν τον τρόπο μπορούμε να προστατεύσουμε το περιβάλλον και όχι μόνο, έχουμε και μια ευθύνη στον πολιτισμό μας, να τον συντηρήσουμε, να παραδώσουμε ό,τι μας παρεδόθη και επιπλέον είναι και εθνική οικονομία. Ναι, η πρωτογενής παραγωγή, η οποία έχει παραμεληθεί πάρα πολύ νομίζω τα τελευταία χρόνια, η πρωτογενής παραγωγή είναι τεράστια και ο τρόπος της επεξεργασίας θα έπρεπε να τον δούμε με ένα μάτι πιο κριτικό, με ένα μάτι βαθαίνοντας από το παρελθόν, χρησιμοποιώντας τις σύγχρονες τεχνολογίες. Αυτά και έπειτα συνέχεια. Ευχαριστώ πολύ.
Ευχαριστούμε πολύ την κυρία Τριχοπούλου για την εισαγωγή στην μεσογειακή δίαιτα και προσβλέπουμε στη συζήτηση να κοιτάξουμε και τι σημαίνει μετά την κλιματική αλλαγή όσον αφορά τη δυνατότητα να συνεχιστεί αυτή η μεσογειακή δίαιτα. Now it's my turn, and I would like to, let's see if we have the first slide. 14 minutes. Yeah, okay. Those of us who work in the space program have a hard time talking without slides. So here's my first slide, and what you see is some of the beautiful pictures that were actually taken by the Voyager spacecraft almost 3 decades ago. Just to make the point that, in fact, we know about the planets. We know a lot about the planets. In this particular slide, you also see in the upper left-hand corner our neighbors, Mercury, Venus, and Mars. And you see, of course, how small they are. But that's not the point. I also wanted to show you that, in fact, we have actually been there and landed in just about every one of them, and we know about the atmosphere. And without further ado, I want to show you the next slide, and it doesn't seem to be coming. Can you please help? Oh, here it is. Well, Professor Synolakis showed you a version of this, and this was my attempt also to describe what, in fact, means the greenhouse effect. But the reason I saw that is to point out that it's not just carbon dioxide, it's also water vapor, and most importantly, it's methane. And we got lots of methane in the atmosphere. A lot of it, by the way, produced like 25% by the animals that we use in our diets. And it's quite key to all that we do. So, in the next slide, I just want to show you a picture. Oops, sorry. I'll go one back. We missed one. Here it is. I went over it. This is the first picture of Venus from the Mariner 5 spacecraft that was there, as you can see, you may be able to see, in 1967. I was part of that mission. And as you can see, no one could see anything about the details of the surface. This is all the atmosphere. And the reason is that is CO2, carbon dioxide. And you see that the surface temperature is 462 degrees centigrade. Professor Synolakis pointed out how all the prediction was about the greenhouse effect. I have to say that, at least in a middle order than his, even at the beginning of the space program, nobody really talked about that seriously. But then people saw this picture. They say, oh, what's happening here? Ah, it's all carbon dioxide in the atmosphere. Ha, it's probably right. There is greenhouse. And look at what happened. The atmosphere in a sister planet, which otherwise would have been a little higher than the surface temperature of Earth, is 462 degrees centigrade, more than the melting temperature of lead. So, if we now go back to the slide that I was trying to show you before, you probably cannot see the numbers, but here what I'm showing is our neighbors, Venus and Mars, essentially, and Mercury. And I want to point out to a couple of numbers that are very important. I highlight the temperature, and you can see what I said before about Venus, that is 462. As we know, our Earth ranges from minus 89 to the poles to up to 58 at the equator. Mars is minus 87, and in the summer at the equator is like 30 degrees. So, what else can we say, however, about the pressure? The pressure at Venus is 92 times as large as that of Earth, 92 atmospheres, as we say. And below that is the atmosphere, which I have already indicated. It's mostly CO2. It has a tiny bit of nitrogen. At Earth, as we know, is nitrogen, but quite a bit of oxygen. And on Mars is CO2 and some traces of nitrogen and argon. But note how small the pressure is on Mars. It's only 0.6% of that of Earth. And since the atmosphere is mostly carbon dioxide, you can imagine that a human being cannot walk on the surface of Mars and breathe the atmosphere. It's as simple as that, and it cannot be protected. But it's worse than that. I'm addressing now the issues of what other planets have told us. And what I'm showing you is on the right, the Earth's magnetosphere. You might say, what is that? It's that part of space that is dominated by the Earth's magnetic field, and it goes as high as 60,000 kilometers from the surface of the Earth. As you know, our atmosphere extends to 50 to 90 kilometers if you include the ionosphere. So what happens is you see these lines that are kind of hitting the boundary of the magnetic field. That is a gas that's emitted by the sun continuously. It has a temperature of 1,000,000 degrees. And our magnetic field is deflecting this gas, and it goes right past us. It doesn't touch our atmosphere. It doesn't get anywhere close to the surface, needless to say. By contrast, right next to that on your left is Mars. And what do you see there? Well, you don't see a magnetic field. And what also you see is that this 1,000,000-degree gas of ions and electrons actually impinges on the atmosphere, or whatever gases there are and it ionizes them, and once it ionizes them, it drags them out into space. So Mars had probably as much water as our Earth back 500 million after the formation of our solar system. We know that because we see the remnants of ice on North and South Pole and under the surface and so on. But after that, it lost its magnetic field for some reason which nobody understands. They say where the dynamo stopped. I'm not going to get into that. But the fact of the matter is that then this million-degree solar wind essentially killed the atmosphere of Mars. Here we are then. On Earth, we have all this protection. On Mars, there is none. And of course, no life activity, biological activity could have developed on Mars except whatever microbial biological activity might have occurred in the first 500 million years. This brings me to the final point. The final point is, ladies and gentlemen, that when Elon Musk and others say that we're going to colonize Mars, that's a midnight summer's dream. This is ridiculous. We can't go on Mars and breathe. And the second point is that it is continuously bombarded by cosmic rays, radiation that penetrates right through our bodies and does biological damage to the chemistry of our body. And the third problem is that occasionally the sun has a big explosion, and the ones that are absolutely killing are occurring at least one every 10 years, sometimes every 5 years. But if a human was walking on the surface of Mars, they would be killed within a few hours. And our biggest challenge these days, NASA and other agencies are working on that feverishly, is to have the so-called predicting space weather, just like we're able to predict Earth weather and avoid the ill effects to our infrastructure. And I will close with the final slide just to point out that, it's not just the radiation that I pointed out. I'm listing here 3, 4, 5 titles. After gravity, physiological changes, balance disorders, fluid shifts in the body, cardiovascular deconditioning. Then, I mentioned space radiation. Then, distance from Earth. What's going to happen if some person gets ill on a spacecraft? We can't just send a doctor to take care of them. And then there is a hostile closed environment. There is the environmental carbon dioxide levels that build up within the spacecraft, and it's toxic. And of course, the water and food is another issue. So, anybody who believes Elon Musk that we're going to colonize Mars anytime soon, let's forget that. There is absolutely no Noah's Ark for us to pile on and go someplace else. The only spacecraft we have is called Spacecraft Earth, and we are the passengers. And if we don't take care of it, that's the end of the human race. Thank you.
Tell us something about the runaway greenhouse effect on Venus, because you're one of the people that discovered it. So it's very important to understand what happens when you get out of control and you have a runaway greenhouse effect.
Well, clearly that so-called runaway that Professor Synolakis says, it does exist on Venus. I mean, it's mostly carbon dioxide, and it's gotten to the point where you have 460 degrees temperature. Nobody really knows exactly how it happened. However, we now have, through synthetic aperture radar, we have pictures of the surface of Venus. And what do we find is that there are lots of volcanoes, lots of lava, and all of that gas, initially in the early part of the solar system, nobody knows whether it was 500 million years, a billion years or so, produced enough gas that after a while, essentially, you couldn't reflect any of the sun's heat back into space. And that's the runaway effect, and of course, the temperature gets to a point where it's totally intolerable. So, whether the curve that Professor Synolakis showed you with a big jump in the presence of carbon dioxide in our atmosphere is the beginning of that, we don't know. But that's why, of course, all our experts say that we've got to limit the carbon dioxide production on the surface of the Earth and limit it fast. Thank you.
May I ask you something?
Yes, ma'am.
Όπως το λέει και το τραγούδι, η μάνα μου είναι η γη, εγώ θέλω να σας πω γιατί έγινε το carbon dioxide τώρα και μιας και είμαστε σε αυτόν τον υπέροχο μοναδικό ελαιόνα, ότι η ελιά απορροφά πολύ περισσότερο διοξίδιο του άνθρακος από ό,τι παράγει. Σε εσάς λοιπόν κύριε καθηγητά μου ο λόγος τώρα.
So is the conclusion that we should plant olive trees all over the earth?
The conclusion is that not only along with governments, there is so much we can do along with our personal food choices that will help us save the earth. And thank you very, very much for pointing it out, because like you said, there is absolutely no plan B. Thank you very, very much.
Okay.